Have you ever really stopped to wonder how a machine actually learns to think? Not in a sci-fi way, but like, what's the actual architecture? Well, today we're taking a look under the hood. We're going to journey from the perfect, logical world of a chess game all the way to the messy, unpredictable reality of a self-driving car. So let's just start with the big one. How do you build a machine that can actually think? I mean, this isn't just a philosophical question anymore. It's one of the biggest engineering challenges of our time. And today, we're going to break down the core principles, from the very first ideas right up to the cutting-edge tech we're seeing today. And this quest is definitely not new. It really got started with Alan Turing, asking that very question way back in 1950. And it's been a real roller coaster since then. You had the deep freeze of the AI winter in the 70s when funding just dried up, and then these incredible highs, like when Deep Blue beat the world's best chess player. It's all led to this absolute explosion of capability that we're all living through right now. Okay, so if you want to build a thinking machine, you've got to have a blueprint, right? Well, in the world of AI, that blueprint is something called a rational agent. This is the foundational concept, the absolute bedrock for creating any machine that can perceive the world, reason about it, and then act intelligently. A rational agent is actually a beautifully simple idea. I mean, think about a smart thermostat. Its sensor perceives the room temperature. If it gets too cold, its actuator kicks on the heat. And what's its goal? To keep the room at the temperature you set. It perceives, it decides, and it acts. And believe it or not, from that simple thermostat to a mind-bogglingly complex self-driving car, this is the fundamental loop of all artificial intelligence. All right, let's dive into the first major approach for building these agents. Early on, AI researchers treated the world like it was a giant game of chess. Everything was known. The rules were fixed, you could see all the pieces, and the goal was crystal clear. The challenge wasn't figuring out the world. It was about finding the absolute best sequence of moves within that perfect, predictable world. So, in this perfect chessboard world, two main problem-solving strategies popped up. On one hand, you have systematic search. Think of it like checking every single possible route on a map to guarantee you find the shortest one. It's methodical, it's perfect, but man, it can be slow. On the other hand, you have local search. This is more like starting at a random spot on a mountain and just walking uphill, hoping you end up at the highest peak. It's way faster, but it doesn't guarantee you'll find the absolute best spot. Now, an algorithm like A-star search is so clever because it does both. It doesn't just look at the distance you've already traveled. It also makes an educated guess, a heuristic, about how much farther you still have to go. By combining what it knows for sure with a really smart guess, it intelligently prioritizes the most promising routes. It finds that best path without getting lost exploring every single dead end. And this really highlights the core philosophy of these early algorithms. Fail fast. It isn't just about finding the right answer, it's about eliminating the wrong ones as quickly as you possibly can. By tackling the hardest, most constrained parts of a problem first, the system avoids wasting tons of time on paths that were just never ever going to work. It's really smart. Now, this classical approach, it's elegant, it's powerful, and it works perfectly, but only in a perfect world. And that right there is its fatal flaw. So what happens when the world isn't a perfect chessboard? Well, this was the moment the entire field of AI had to make a massive pivot, away from perfect rules and towards a new reality of messy, imperfect data. Because, let's be honest, the real world is not a chessboard. The rules aren't always clear, information is often missing, sensors can be wrong, and sometimes things are just random. A system that's built on pure, rigid logic completely falls apart when it faces that kind of uncertainty. A totally new way of thinking was needed. This led to the rise of machine learning, but it brought its own central challenge, generalization. You can see the problem right here in this chart. The model absolutely aces its practice test, the training data, but then completely bombs the final exam when it sees new data for the first time. It's basically memorized the answers instead of actually learning the concepts. We call this overfitting, and it's a huge problem to solve. So, what's the most common solution? It's called supervised learning. You basically feed the algorithm a ton of labeled examples, like, say, all of your past movie ratings, and it starts to learn the underlying patterns of what you like. The goal is for it to get so good at understanding your taste that it can accurately predict how you'll rate a brand new movie it has never seen before. For decades, machine learning was chugging along, but it had its limits. Then, around the 2010s, a revolution happened: deep learning. Fueled by absolutely massive datasets and incredibly powerful computer chips, this new approach started using these complex architectures called neural networks, which are loosely inspired by the human brain, to achieve just incredible results. And here is just a beautiful example of how it works for images. It's a convolutional neural network, or CNN, and it builds understanding layer by layer. The first layers might see really simple things, like basic edges and corners. The next layers combine those into more complex shapes, and then the layers after that combine those shapes into objects, like an eye or a nose. It's almost like a digital artist, starting with a rough sketch and slowly building up to a detailed masterpiece. But what's amazing is this goes way beyond just images. Deep learning can actually learn the meaning of words by plotting them as coordinates in a giant multi-dimensional space. And in this space, the relationship between words becomes geometric. So the direction and distance from the word man to woman is almost identical to the vector from king to queen. It learns these abstract concepts, like gender or verb tense, or even a country's relationship to its capital, all just from reading text. This leads to something that honestly feels like pure magic. You can do math with concepts. So for example, what happens if we take the vector for king, subtract the vector for man, and then add the vector for woman? What do you think you'd get? The answer is the vector for queen. Let that sink in. The machine hasn't just memorized definitions. It has learned the underlying relationships in our language so deeply that it can actually reason by analogy. This was a profound, jaw-dropping moment in the history of AI. So far, we've talked about agents that learn from these nice, static, labeled datasets that we give them. But what if an agent has to learn on its own, completely from scratch, just by interacting with the world? Well, welcome to the wild frontier of reinforcement learning. Let's make this really simple with something I call the cake problem. You've got cake, you love cake, but you have a roommate who might eat it overnight. If you eat all the cake right now, you get a huge reward today, but you get 0 tomorrow. If you save some, you risk your roommate stealing it. You have to make a decision now to maximize your total long-term cake enjoyment, even with an uncertain future. That right there is the entire puzzle of reinforcement learning. Now, the formal framework for this is called a Markov decision process, or MDP. Don't let the name scare you. The states, that's just how many slices of cake are left. The actions, that's how many you eat. The transition probabilities, that's the chance your roommate eats a slice. And the reward is your delicious cake enjoyment. The agent's entire goal is to figure out the best policy, the best strategy for what to do in any state to get the most possible cake in the long run. And that is the absolute beauty of it. The agent doesn't need to be told the rules of the cake game. It just needs to be able to act, see what happens, and get some feedback, either a reward or a penalty. And through millions and millions of attempts, it learns for itself what the best strategy is, discovering things we might never have even thought to teach it. But hang on, what does maximizing reward even mean? This is where we have to define the agent's personality through what's called a utility function. A risk-averse agent, maybe like a self-driving car, will always play it safe. It prefers a guaranteed good outcome over a risky gamble. But a risk-neutral agent only cares about the long-term mathematical average. We, the designers, have to be the ones to decide what values to encode into these machines. And that brings us to the final, and I think, most critical question. We set the goal, maximize profit, win the game, drive safely. And the agent, using these incredible architectures we've talked about, discovers its own path to achieving that goal, often developing behaviors we never could have predicted. So when an agent learns its own way, who is ultimately responsible for where it ends up? That's the question we're all going to have to answer as these architectures of intelligence become ever more a part of our world.